In this video, we're going to go over another quick example of the conservation of angular momentum, this time for planetary orbits. So in another problem, we went over a spinning skater. So that's an example of conservation of angular momentum in rotation. And this is an example of conservation of angular momentum in a planet revolving around a star. So in this case, we have Mercury. So the problem states that Mercury has the most eccentric orbit in our solar system, with its closest approach to the Sun at a distance of 47 times 10 to the 9 meters, and its furthest distance at 70 times 10 to the 9 meters. If Mercury has a velocity of 59 kilometers per second at the closest approach, we want to know its velocity at the furthest distance. And then we're given the mass of Mercury as 3.3 times 10 to the 23 kilograms. So for planetary orbits, these are actually slightly elliptical and not perfect circles. And in our solar system, Mercury has the most elliptical orbit, meaning its distance from the sun varies the most. So at its closest approach, we have a distance here we'll call this RC for the closest approach. And then at another point in its orbit, it's going to be farthest away. And we'll call this RF. And then all of the distances in between are in between RC and RF. According to Kepler's second law, the velocity at these different points is going to vary as well. But our total angular momentum will stay the same. So angular momentum is given by the mass. The mass is the same at any point in the orbit. It's just the mass of Mercury. Then times the velocity, and then times the radius or the distance to the sun here in this case. So for our problem, our C is equal to 47 times 10 to the 9 meters. Our F is 70 times 10 to the 9 meters. And then we have the mass of Mercury right here, and we're also given the velocity at the closest approach. So we'll call this VC, and that is 59 kilometers per second. But the distances are in meters, so we want to go ahead and convert this to meters per second so that everything is consistent in our equations. So kilometers per second, that's just going to be multiplied by 1,000 to get meters, right? So 59 times 10 to the 3. 10 to the 3 is 1,000, and that's meters per second. So we can set up our equation for conservation of momentum. LC is going to equal LF. So the angular momentum at the furthest distance is going to equal the angular momentum at the closest distance. Because the distance is going up at one point, that means the velocity is going to go down since the mass is staying the same. So M is just the mass of Mercury times VC times RC has to equal the mass of Mercury times the velocity at the furthest point times the distance at the furthest point. Now we have the mass on both sides. If we divide through by m, this is just going to cancel out. So our velocity is not dependent on the mass, it's dependent on the distance, right? So let's go ahead and we'll divide both sides by RF to get that. VF, the velocity at the furthest distance, is going to equal VCRC divided by RF. And now we can just plug in the values. So that's going to be 59 times 10 to the 3 meters per second times 47 times 10 to the 9 meters divided by 70 times 10 to the 9 meters. And that's going to give us a velocity of about 40 times 10 to the 3 meters per second. Or if you want to put that in kilometers per second, that'll just be 40 kilometers per second. So as you can see, the velocity is lower when it's further away and higher when it's closer to the sun. So hopefully that was helpful, and if you want to see the other example of conservation of angular momentum for the spinning skater, both of these are really common conservation of angular momentum problems. So if you want to see the other one, it should be on the screen. So thanks for watching, and let me know if there's anything else you guys would like to see.